This video is going to focus on the properties of exponents, at least a couple of them. There's quite a few, so we'll split this into two parts here and just do the first couple in this first video. So the first one is the product of common bases. Product obviously means multiplication. Common bases, I mean that look at the x's are the same. So we can say if we have common bases, we'll probably be able to do something here. The example that we have here is x squared next to the fifth. Just think of x squared as x multiplied by x. That's technically what squared means. And then x to the fifth, same thing. It's just 5x's if you actually chose to write it all out. And then this multiplication dot is in between those. So notice how it's x multiplied by all the way across. It's all multiplication. Because it's all the same symbol, we can condense this all and say, well, that's actually just x to the seventh now, because multiplication repeated is a power. So if you have a multiplication between these two, you can actually list it all out and write it as x to the seventh. The shortcut would be just to add the powers together, because you have 2x and then 5 more later for a total of 7. So if you have a common base and you're multiplying them, you may add the powers together, and that's the shortcut way instead of actually writing all of this out every time. That'd be a big pain. Now, something to notice here is if you had a plus in between here, like x squared plus x to the fifth, wouldn't quite be so simple, because x multiplied by x is here. You again have the 5x's multiplied over there, but instead of a multiplication linking them here, you have a big plus sign. So multiplication plus multiplication, that breakup of operations that change there means it's not quite so straightforward. I can't do any of these shortcuts. I can't simplify this, unfortunately. So this one you couldn't do anything with. Now, if you did have something like this, let's say you had like x to the third plus x to the third, I can't make this x to the sixth, but I could say that I have 2 of those. So you can add things together as long as they perfectly match, but you can't add them if they don't quite match, because there's no common symbol throughout. So on the next slide here, we'll do a couple examples. X to the fourth, x to the seventh. Just remember that when you have parentheses, technically no symbol between them means it's implied multiplication. So you could put this in a different way if you chose to. This is really just x to the 11th if you add the powers together. Problem 2, we have x multiplied by x to the sixth. You could write this first power here if you wanted to. We usually don't because it's not needed, but it's kind of implied that this is x to the first. There's 1 x sitting there, 6 more there, so 7 total. In this part here, I often see mistakes on something like this. It's kind of silly, but essentially picture that 2 to the fourth is 2 times 2 times 2 times 2. This is 3 2's as well, which means you have 2 to the 7th. Sometimes I'll see people write this as 4 to the 7th, which is kind of logical. I mean, you think, like, multiply the 2's and I add the powers, right? Well, you have 7 2's, so that works. You don't have 7 4's, so that's out of it. So just silly mistake there, don't multiply the bases. And picture what I did here, x to the fourth, x to the seventh. It's still x, it's just I changed the power. Same here, just still x, just different power here. So never change the bases, even if it's a solid number. If you want to actually multiply this out, this would be 128. So you can multiply it out. You could even have done it right in the beginning. This is 16, this is 8. Multiply together, we'll still get this. But you should never make it a different base and also change the power. That's never a good combo there. And the last one here is not a whole lot you can do. You're kind of stuck. You have different bases here, so they have to stay separated. This is actually the best way to leave that one. This doesn't really help at all. Okay, so the next one that we'll do is exponents on a group. Notice how it's got parentheses here. That's what I mean by a group. It's just some items that are collected together inside of parentheses. So the first type here is if you have a power already established on a base, and then outside of the group is another power waiting to go into effect here. In this example, we'll show what's happening here. A third power, again, means multiply by yourself 3 times. So x squared multiplied by x squared multiplied by x squared would be what that means. We actually just saw this happen. Essentially, that's 2x's with another 2x's with another 2x's. It's all the same operation. It's all multiplication, so you can add up the powers there and say I have a total of 6 x's listed throughout. Had you added all these 2's, you would have gotten a 6. Had you multiplied these together, you would have gotten x to the 6 right away. So the shortcut there is to multiply powers. If you have a base to a power, and then you're raising it again to another power. So look at the slight difference here, just make sure you see the difference. 2 different x's being multiplied versus 1 singular x with different powers on 1 singular x. These two are actually even simpler. The idea is if you have a group and you have a power on it, everything in the group must be affected by it in some way or another. If there's a multiplication dot here, you can essentially send the power to both items. It's not actually the distributive property, but it's kind of the same idea. So we can write this as a to the n and x to the n. Same with a fraction. A fraction is technically just multiplying by a reciprocal, so the same property applies here, x to the n over y to the n. So you can just apply that to everything here. Now I did notice, or I did mention that the multiplication dot here, it has to be multiplication, nothing else works besides multiplying by a reciprocal here. Notice what happens in this scenario here. If I have multiplication versus a plus. So if you picture squared, that means multiply by yourself. So you could say, well, that's 3x multiplied by 3x. Once again, we're noticing that we have multiplication, multiplication, multiplication. It's nothing but multiplying here. So let's just go ahead and do it. 3 times 3 is 9. X times x is x squared. So we could have just done squared and called it a day. Versus here, if you write this out, that would be 3 plus x multiplied by another 3 plus x. Once again, we're seeing this issue where we have a mix of operations. A plus, a multiplied, a plus. There's no real good way to simplify this. Other than you've maybe heard it called the FOIL method before. It's really just a distributive property. You could distribute the 3 to both parts, 9 plus 3x. Distribute the x to these, it'd be another 3x plus nx squared. So this is a little more of a pain. That's why it's kind of nice when there's only a multiplication here. With a plus, you have to do all the extra work there. So let's do a few more practice examples, and that'll be it for this. We've got x to the 4th to the 7th. This is one singular base raised to a power. We can multiply these powers together. So 28th power on the x there is all you need to do for that. In 2, again, we're going to send the power to both bases inside of here. 3 to the 4th, x to the 4th, and if you wanted to, you could go ahead and change that into a simpler number, 81 instead of 3 to the 4th, and then x to the 4th is still as it was. The next one here looks a little more complicated, but it's really not that bad. Same thing, you're basically sending the power to both items here, including the number. So negative 5 squared is a regular 25. Remember, a negative squared is a positive, because a negative times itself does turn back to being positive. X to the 3rd squared, you're going to multiply those powers together. That'd be x to the 6th. Y to the 6th squared, again, a base with a power, you're going to multiply those powers together. That'd be y to the 12th. Final one here, again, we are sending the power to every item top and bottom of the fraction. The 2 gets it, the x gets it, so does the y. So 2 to the 5th, x to the 5th over y 3rd to the 5th. And let's just go ahead and simplify a little more. 2 to the 5th is 32. X to the 5th is good as it is. These two powers can multiply together, and we're left with y to the 15th. So just a quick recap here, we did two things mainly. If we had two different groups there, we have a multiplication between. As long as the bases match, we can add their powers. And we also talked about if we have one singular base to multiple powers, you can multiply those powers together. If we have a group inside of parentheses, you can send the power to every item.